Hi, and welcome to a brief presentation of our work on ab-initio potential energy surfaces by pairing GNNs with new wave functions. My name is Nicolas Gau, and I'm a PhD student at the chair of Professor Günnemann at the Technical University of Munich. In chemistry, one is often faced with the challenge of molecular modeling, that is, the task of predicting the energy given a molecule. A molecule may be thought of as a 3D point cloud with atomic charges assigned to the nodes. This has many applications, for instance binding energy prediction, molecular dynamics simulation, or reaction predictions. These tools may then be used to discover new drugs, catalysts, or materials. However, one is rarely interested in a single energy in isolation, but rather in the change of energy depending on the geometry. This is where the concept of the potential energy surface comes in, which is a hypersurface over the space of all geometries, which steers the behavior of the atoms by defining energy-favorable states, for instance, if two atoms bond. Unfortunately, to accurately model such a potential energy surface, many energy evaluations are required, which is usually quite expensive. To accelerate this process, surrogate models in the form of graph neural networks have been proposed. They reformulate the energy prediction task as a regression problem by trying to learn the energy surface from data. They do so by exploiting the graph structure of the molecule and exchanging messages between the nuclei. The nuclei then encode the local geometry in the hidden state to predict the energy. This has been shown to be very fast and accurate reproduction of the dataset. However, obtaining the dataset in first hand might be a challenging task and quite time-consuming. Because to obtain an energy value for a molecule, one has to set the Schrödinger equation depicted here above. H is our Hamiltonian, psi is the wave function, R the electron position, and E is the energy value we are interested in. One may notice that this is an eigenvalue problem, where you're trying to find the eigenfunction psi, which is the lowest eigenvalue E. One way of solving this is via something called Variational Monte-Carlo, where we pick some parameterized wave function and iteratively update it until it converges to the lowest energy value. In recent works, the use of neural networks have been proposed as wave function Ansätze, as neural networks have been shown to be great function approximators. This led to very accurate results compared to classical methods, but it turned out to be relatively computation intensive with around 100,000 iterations per molecule. With these two approaches in mind, we naturally come to the question, is there a way we can combine the benefits of both approaches such that we solve many Schrödinger equations simultaneously without requiring any data? To accomplish this, we propose the potential energy surface network, which consists of two parts, a GNN called the MetaGNN and a wave function model. The GNN works similar to the supervised case, where we exchange messages between the nuclei to encode the local geometry, but instead of predicting the energy, we predict the parameters of the wave function. The wave function is then used in the Variational Monte-Carlo framework to optimize the energy and to compute gradients. Since our whole model is end-to-end differentiable, we only need a single training for a continuous subset of the potential energy surface. In our experiments, we could show that our potential energy surface network shows no loss in accuracy in common benchmark geometries, like the hydrogen chain or the nitrogen molecule. Further, if we look at the training times, we find significant speedups of up to 43 times depending on the number of geometries one wants to evaluate. In conclusion, we have presented a framework which enables us to efficiently exploit the correlation between wave functions of similar geometries to reparametrize our model. In our experiments, we found no loss in accuracy, but a significant reduction in training time. This may open the path to more accurate and faster ab-initio methods in the near-term future, accelerating the progress in computational chemistry. And with these words, I would like to thank you for listening to a brief presentation, and we would be delighted if you visit us at ICLR 2022 or on our website linked here.